In this example, we're asked to find a linear polynomial that approximates a function, f of x, near x equals a, and we want the value of the polynomial to match the value of the function at a, and we also want the value of the derivative of the polynomial to match the value of the derivative at a. All right, so this is just a linear polynomial. It looks a little different. We have this a plus b times the quantity x minus a. So it's maybe written in a little strange form, but there's a reason for that. And essentially what we need to do is find these constants a and b. Okay, we're just going to find these constants a and b. So first of all, we want p1, right? P1. Now p is standing for polynomial, and 1, this little subscript 1, is just, it's a first degree polynomial, right? Because it's a linear function, right? The highest power of x is 1, right? So that's why we're using p1. It's because it's a polynomial of degree 1. So it's linear. But first criteria is we want to be able to put in the value x equals a, and we want it to match the value of the function f at that point. So this is what I'm going to do. I'm just going to write a plus b. Now I'm going to put in a for x. So I have a minus a. Okay. And what do I get? A minus a is 0, and I just get a. Okay. So I want this to match the value f of a. All right. So now what I've just found is the value of that a, this a constant. Okay. That a constant is just going to be whatever the value of the function is at a. All right. So a is f of a. Okay. Let me write that off to the side. A is just going to be f at a. All right. Now we want also the value of the derivative to match. So I'm gonna rewrite this so that it's a little easier to take the derivative of. We have a plus, and then if I distribute that b, I have bx minus ba. So remember, capital A, capital B, those are constants that I'm trying to find, and also this a is also a constant, right? It's some value of x. It's some value of x, but it's a constant. All right, so I can find p1 prime of x just by taking the derivative of that and assuming, okay, a is a constant, so the derivative of a is just 0. The derivative of bx is just going to be b, and the last part, b, capital B times a, is also a constant. Well, so that's good. The derivative of this linear function, since it's linear, you would expect it to be a constant. And so it's just the slope of the line, right? So the slope of the line is b. All right. Now I want p1 prime at a, right? Which is b, no matter what x is, right? Because it's just a constant. I want that to match the derivative at a. Okay, so let me write that up to the side. So now we found the value of b. B is f prime at a. I know this seems a little strange, right? But let's write what we have now. What we have now is that this p1 of x is equal to, now I'm going to replace a with f of a, and I'm going to replace the b with f prime of a, and then we have x minus a. All right, so what we have here is a linear polynomial, and this is the linear approximation. This is essentially what we did in the last example. We took the position that we were at 2 hours, and then we took the rate times the change in time to figure out where we were at a different point in time, right? So we're just taking the value of the function at a and taking the rate at a times the change in the x value. Okay, So this is a linear approximation. Now, this is exactly the same also as the point slope formula, right? Because the point slope formula, let's see, right off, it says y minus y1 equals m times x minus x1, right? Where x1, y1 is a fixed point, m is the slope, and that's the point slope formula. But if I rearrange this, I can subtract f of a from both sides, and essentially I have the change in y is equal to the slope times the change in x. So it's the same as the point slope formula. So let's take a look down here. This is the summary of what we have here, that we can use this linear approximation to estimate values of f of x, essentially. So essentially what we're saying here is that this is approximately equal, maybe I should make that, this is an approximation of f of x, right? And it'll be a decent approximation as long as the difference between a and whatever x we put in is fairly small. So there we go. There's our derivation of our linear approximation. Now it's nothing new. Like I said, it's just a tangent line. It's a tangent line. And this formula really is just the same as the point slope formula. So all right, well, I'll meet you for the next example in the next video.